From Diamond Light Source, this is the Diamond Podcast.
Hello, Happy New Year and welcome to the Diamond Light Source Podcast. This month, a look back at 2010 to see the changes and developments made at the facility, as well as key pieces of research that took place, including this minuscule discovery with large-scale repercussions.
What's basically happening is the microbes are eating the various minerals in the rocks as a source of energy, and they contribute to the weakening of the rocks and eventually to its large-scale deterioration and collapse. And that's how a little creature, a micron in size, can actually contribute towards erosion on a kilometre scale.
Charles Cockell will be explaining just how these microbes have such an effect. Plus, we also try to solve some challenges of fundamental chemistry.
The one we'd love to do is to try to make a metal to xenon bond. The xenon is incredibly unreactive. It's actually being able to identify and characterise a bond to xenon. It's almost one of the holy grails of chemistry.
Neil Champness takes us on his search for the Holy Grail later in the programme, when we also bring you the latest news and events from Diamond. So all this in this January edition of the Diamond Light Source podcast, with me, Meera Senthilingam.
The Diamond Podcast. For more information, look us up online at diamond.ac.uk/podcast.
2010 saw many changes and improvements to the Diamond synchrotron, as well as good news about how it will continue to improve in the future. Diamond's Physical Sciences Director, Trevor Raymond, explains more about the synchrotron's journey to completion, as Diamond gears up for Phase 3.
This is important for Diamond because it's always been seen as a three-phase development project. In phases 1 and 2, we built the machine and are close to completing 22 beamlines. And in phase 3, we'll add a further 10 of these beamlines. So phase 3 is going to improve our capacity for doing science and engineering and technology by about 50%.
Now, how are these phases actually broken up, though? So what makes phase 1 and 2 and 3 separate?
Well, the way that a synchrotron operates is that it provides a number of quite independent scientific facilities that we call beamlines, which just simply describes the fact that the light is a beam and it comes down a line of equipment. But perhaps a better way of thinking about these is as independent scientific laboratories. Every laboratory is designed for a specific task, and if you want to have a broad scope, then you need to have a large number of beamlines because each one is a very specialized, designed for a particular scientific purpose. By adding a further 10 of these beamlines, we're improving the scope of what we can do enormously. I'd like to give you a couple of examples. There are a series of methods that have been developed outside of synchrotrons in other areas of science called high throughput, where you deliberately employ automation, robotics, artificial intelligence to squeeze the very most out of your instruments. And this does two things. First of all, it enables more people to access the facility. But not only that, it enables you to do things you couldn't dream of doing before, simply because it would take too long. You can ask questions that are more difficult simply because you can do more experiments more quickly. Phase 3 gives us increased volume, and it gives us hugely increased scope of what we can do.
You mentioned the light generated by the core synchrotron itself is what changes and is altered for each beamline. But in 2010, a change was actually made to the core synchrotron and the way it produces its light.
Yes, it was. Now, if you imagine a synchrotron looking down from above, the way we normally explain it is as a many-sided coin, a 24-sided polygon. That gives you the impression of the electrons traveling in a straight line between magnets that steer the beam. So the electrons will go in a straight line and then be steered around a corner. They'll do that 24 times altogether to go round. And then on the long sections of this polygon, we put what we call insertion devices, which are purpose-built magnetic structures that produce the light that we want. But electrons are not really like that. All electrons are negatively charged, and if you just put them together and leave them alone, they'll repel each other. And so what that means is that as the electrons are traveling along in a straight line, they're also moving apart from each other, which means the beam gets bigger. So part of the structure of the machine are components to refocus the beam back down to a very small point. And so what you have to imagine is that not only do you have the electrons moving in a straight line, but they're diverging, and then you refocus them. Now, in the original structure of diamond, they were arranged so that the electron beam was focused at the center of each of these straight sections, because that's where we would put the insertion devices. Some of these straight sections are actually quite long. They're 5 meters long, and there is in fact space to put 2 of these insertion devices. So in principle, you could have 2 sources of light rather than 1, and that would mean that you could build 2 beam lines rather than 1 beam line. However, the fact that the electrons are focused at the center means that if you have 2 insertion devices, they've both got to be off-center, and neither is in the optimum position. So what they've done this year is they've changed the structure of the machine such that they can insert additional focusing lenses at the end of each of the straight sections and also in the middle of the straight section. And so that now the electrons, as they enter this straight section, are focused very early on. They diverge, and then they're focused back in again on the straight section and then out. So it becomes, instead of having 1 dip in the middle, it's got a double dip.
So essentially, this is just leading to more regular, focusing of electrons along their route around the synchrotron.
More specialized. I won't say it's regular, but it's more specialized. The take-home message is the light that is delivered out to the users is going to be brighter and more flexible.
And, you mentioned that Diamond's priority is always the users that come in and actually use the facility for their research. And you actually reached a milestone in 2010 in terms of, the research and the publications resulting from this research.
Yes, we did indeed. We reached the milestone of 1,000 publications produced from users and from people who work at Diamond. And that's 1,000 publications since the start of Diamond. We started operating in 2007.
Are there any particular papers that are particularly noteworthy or stand out in your memory?
There have been some very interesting studies carried out at the University of Leicester where they've been looking at the fate of depleted uranium, an environmental study. There have been work on lead-free ceramics to make piezoelectrics. That's an important material science application. And there have been work carried out at Imperial College where they've been able to solve a 20-year-old mystery about the way that HIV attacks the body.
Well, Trevor, everything you've mentioned just reiterates the fact that such a wide variety of scientific disciplines are researched at Diamond. But another important aspect of the facility is the fact that you develop workshops and you have a great deal of outreach.
Yes, that's true. Diamond exists for people who don't use it as much as it does for those who do. We're now a mature facility, and we are keen to attract a very large number of new users and experienced users. And one way we do that is we host meetings. These meetings range from training, meetings that simply liaise with users. We bring them in, listen to them, listen to their concerns. And we host external scientific societies, for example. And, of course, we welcome lots of visitors from the local area on our Inside Diamond Days.
And we'll be hearing more about these outreach activities with Sarah Boundy later in the programme. That was Diamond's Physical Sciences Director, Trevor Raymond. Now, as Trevor mentioned, Diamond creates these beamlines and facilities to aid scientists in their work. One such scientist is Professor Charles Cockell from the Open University. He's been focusing on the problem of coastal erosion and the causes behind this increasingly problematic natural event. But whilst many of us are aware that tides and waves can damage rocks on our coastline and cause erosion, Charles has been focusing on a much smaller cause that seems to be having grand effects.
Erosion is a big problem. I mean, a large percentage, well over 15% of the UK's coast are subject to coastal erosion. Now, this is a natural problem, of course. Wave action, tidal action causes coastlines to erode, but of course it's become more of a problem recently given concerns about rising sea level, also human manipulation of coastal regions that can cause some areas of the coast to erode more quickly than other areas. Tidal breaks and these sorts of things can cause artificially fast rates of erosion.
But you've been particularly looking at an area of the coast along the North Yorkshire coastline.
That's right. This is an area where there are shales that are weathering quite quickly.
So what's been thought up until now about the causes of this erosion on that coastline?
Well, up till now, people have focused on the large scale. So they've mapped the faces of these cliffs and seen large-scale rock falls and really begun to understand the physics of how erosion occurs down to the centimetre scale. But it's still not really understood what's happening at the very small scale, literally the micron scale, the scale of microorganisms. How do those chemical processes cause rock erosion, and what sort of processes might be involved in causing coastal erosion? And that's where we come in, because, of course, microbes are very, very small, about a micron in size, and so they might be relevant to erosion at these very small scales.
So the coastline you've been looking at is made up of shale, as you've said. So which microbes are thought to be having an effect here, and what are they actually doing in this area?
Well, we know that microbes can oxidize iron in shales. They oxidize it and turn it into iron oxide, rust, basically. And those new minerals that are formed can form in the cracks of rocks and contribute to their degradation. But in our rocks, we found that very few of the iron oxidizers that we found, or in fact very few of the microbes in that environment, were related to things that have been studied before. So we think there's a novel microbial community in there that's responsible for weathering the rocks. But what's basically happening is the microbes are eating the various minerals in the rocks as a source of energy. And in the process, they're breaking down the rocks, but they're also producing new minerals that are formed on the rock surfaces. And they form in tiny fractures inside the rock, and they contribute to the weakening of the rocks and eventually to its large-scale deterioration and collapse. And that's how a little creature, a micron in size, can actually contribute towards erosion on a kilometre scale.
So what microbes are these, and how much are they thought to be contributing to erosion on this particular coastline?
The varieties of microbes are very large. We've extracted the DNA, we've looked at the community, and there's all sorts of microbes in there that we don't really understand and we don't know what they're doing. What their contribution is the big question. We know they're there, but we don't know which ones are active in breaking down the rocks and how much they contribute towards forming the minerals. Because what we do know is that weathering can also occur chemically without the microbes. And so the next challenge is really to understand the contribution of the microbial community.
Let's go a bit into how you've been looking into the effects then of these microbes, or perhaps even how they're actually working. So this is where you've been using the diamond synchrotron. But an interesting aspect is that you've been using quite a few different techniques at Diamond to look at very many aspects of the microbes.
That's right. We use a number of methods. There are biological methods where we extract the DNA and we try and understand what the microbial community is doing inside the fractures and how they're distributed and what types of microbes are there. Essentially, we're asking the question, who's in there? But we're also interested in understanding the minerals that surround them. What are those minerals? What structure do they have? Could they have been produced by microbes? And that's where Diamond comes in, because we can use Diamond to map the different types of iron minerals on the surface of the rock, try and understand their relationship to the rock surface and what characteristics they have. And so we've been using Diamond to map the surface of the weathered fractures in the coastally eroded cliffs. And we will then go on and see whether microbes can produce these sorts of minerals.
How useful then would you say these techniques are?
They're extremely important because they allow us to really probe the structure of the minerals. It's one thing just to know what their composition is, but we want to know their structure. We also want to know how they're distributed on the surface of the rock. Are they localized in one place? Are they evenly distributed? That tells us something about the way in which the rocks are breaking down.
So how would you summarize then your findings so far? And I guess at the end of it all, what's the aim? I'm assuming we can't obviously prevent it. What could be done using this information?
In terms of stopping these things, it's interesting you say that. The assumption is that we can't do anything about it. The microbes will just eat the rocks. But in fact, there are fascinating questions about if you know which microbes are weathering these rocks, could you slow them down? Is it possible even that as sea level rises, salt water will actually kill off some of these different types of weathering microbes and slow the process down? Or will new types of microbes take over?
Another important thing to consider is the fact that the impact of these microbes isn't just limited to the erosion of the actual coast. There's greater effects spanning from this.
Yes, absolutely. I mean, the work that we do gives us much broader insights into the role of microbes in breaking down rocks generally. What role do these microbes play in other shale environments? Shale has a very important role in engineering structures. Many motorway bridges, for example, in the UK are built on shale or near shale, and the microbes that break down shale might have serious implications for civil engineering and civil infrastructure as well. So the study of how microbes break down rocks has quality of life implications as well.
Charles Cockell from the Open University.
Did you know that Diamond's floor area is 45,000 metres squared? That's almost the same as 8 St Paul's cathedrals.
This is the Diamond Light Source podcast, and this month we're looking back at some of the key developments and achievements at Diamond in 2010. So now, let's join Sarah Boundy from Diamond's communications team to find out what happened at the facility towards the end of the year.
Yeah, we recently had a paper published in the Journal of Molecular Biology, which is looking at antibiotics. It reports on the molecular interaction between a protein from a common bacteria called Pseudomonas aeruginosa, which can cause disease in animals and humans. And they're looking at that and the main two antibiotics that are used to combat it.
But what aspect of these antibiotics were they actually looking into?
Well, they used Diamond to solve the structure of the protein bound to the antibiotics to get a picture of how the drugs work against the bacteria. Their results allow them to look at the structure and see ways the drugs could be modified. And one of the problems with Pseudomonas aeruginosa is that it can be particularly dangerous to those who are already ill. It can cause secondary infections. And so they're looking at how to overcome the effect of drug resistance when the bacteria becomes resistant to the antibiotic.
And I guess knowing this then, they could develop new antibiotics or drugs that would be more effective.
Yes, from looking at the structure, they're able to look at ways they can aid the existing inhibitors and come up with new drugs that could be more effective.
The workings of antibiotics are always going to be crucial, but now moving away from life sciences, the main thing about Diamond is that it looks into a whole range of scientific disciplines, including engineering.
That's right. This one's interesting because most of the beamlines at Diamond are looking at samples of things that are absolutely tiny. They could literally fit on a pinhead. But we've had a new development on our JEEP beamline, which is the Joint Engineering and Environmental Processes beamline. And it's the only place in the UK where the internal stresses and strains of components up to 2 tons in weight and beyond a metre in length can be studied at the atomic scale.
So these are much bigger objects than have ever been analysed in the past at Diamond. So what kind of objects are we talking about here? So kind of aircraft designs or aircraft components?
That's right. It's actually the external hutch of the JEEP beamline. It can create molecular scale 3D images of objects such as aerospace and engineering components. The first users were actually from Rolls-Royce, and they were looking at a fan blade from one of their Trent 1000 engines. They were able to use JEEP to look inside the fan blade and measure through all residual stresses without having to remove any of the metal. And Rolls-Royce routinely measure residual stress in their components, and the JEEP beamline is an alternative way for them to do this.
Now, moving back down, though, to small scale, the nanoscale, in fact, you've had users on another beamline as well.
Yes, so we've now got 19 beamlines in operation. Towards the end of last year, we had first users on the beamline for advanced dichroism experiments. We call it BLADE for short. They're investigating multiferroics, which is a class of materials that simultaneously exhibit magnetism and electricity.
So this obviously then has to do with computing and, say, computer chips, as this is how data storage essentially works, which is a crucial part of science and technology to be looking into at the moment.
Yes, they're trying to understand the principles involved and with a view to be able to develop multiferric materials that could work at room temperature. If this could be cracked, they could hold huge potential for new solutions for data storage.
OK, so they were first users on beamlines that were developed last year, but you've also recently had first light.
So this is first light on I-13, our X-ray imaging and coherence beamline. And it simply means that the beamline team was successful in getting the synchrotron light from the main machine into the optics hutch of their beamline. So now they're busy finishing the beamline off, and they hope to welcome first users later this year.
And what essentially is this beamline, or what makes it stand out, and what kind of work will be done on it?
So this one will allow researchers in a wide range of fields to create high-quality 3D images of samples. So things such as engineering components, biomaterials, fossils, organic materials, and energy devices such as fuel cells. And it's a bit different for diamond because its experimental hutch sits 250 metres away from the X-ray source, whereas most of the other ones are within the main building. And we're also developing it a little differently because we've entered into a collaboration with the University of Manchester.
So plenty of development and plenty of new research taking place. But as well as research, another important thing that happens at Diamond, though, is outreach.
That's right. Throughout the year, we try to run lots of events for A-level students and people interested in careers in science and engineering. And in particular, toward the end of last year, we had a day called Engineering Your Future. It was basically a careers day for A-level students who might like to look into taking up a career in engineering. And they did lots of fun things like wiring up a mini RAF pad, programming a space robot to carry out manoeuvres, and they had to build a prototype sturdy base for a wind turbine out at sea. So they did all kinds of things. And we run that event on a yearly basis. And we've got more of that kind of stuff coming up with our particle physics masterclass in March, as well as an Inside Diamond event, especially for A-level students.
And so how can people keep up to date or aware of when these events are happening?
The best thing to do is look at our website. There's plenty of information there about public events. We've actually got the next public Inside Diamond event, which is coming up on Saturday the 26th of March. And registration can be made on our website, which is diamond.ac.uk.
Sarah Boundy from Diamond's communications team. Now that's almost the end of this month's podcast, and we've heard a lot about the microbial analysis taking place at Diamond. But a key point about Diamond is its versatility across all fields of science. One recent and fast-developing area of chemistry is the design and use of metal-organic frameworks. They have potential uses in gas storage and catalysis, but can also provide greater insight into the fundamental workings of chemical reactions, as Nottingham University's Neil Champness explains.
So a metal organic framework is a material, always a solid, which is made by reacting metals with organic molecules which will act as a bridge between different metal centers. So you react the two together and you make a three-dimensional structure. So it will look a bit like a climbing frame. And typically they will have holes within that structure. But more importantly, beyond that, metal organic frameworks are just this subset of materials where you can react metals and ligands.
So essentially it's a three-dimensional porous structure that you can kind of encapsulate things into maybe, but on a very, very small scale.
Yes, absolutely. So the types of sort of dimensions that we're talking about will be sort of 2 nanometers and below, but that is the molecular scale.
What would you say the kind of general aims of these structures are and the general kind of purpose of them?
The beauty of metal organic frameworks is that you can vary the metal that you use. So typically we use transition metals, so things like copper and zinc and things like that. Or you can use lanthanides, okay? So there's a lot of variation there, and they have different properties that they bring with them. But also you can vary the organic molecule a lot as well. And therefore you have an almost sort of limitless library of possible framework structures. A lot of the work is directed towards gas storage. That is a big theme, and our own research group work with Diamond, in fact, on developing hydrogen storage materials. You can use it for trapping carbon dioxide, is another possible direction. There is a lot of interest in developing them for pollutant separation, those types of things.
So essentially you can really just design and tailor these to be specific to the kind of use or the things that you want to look into, really.
Absolutely. I mean, that's the kind of the great desire. And in many ways, that is more true for metal organic frameworks than it is for anything else.
Tell me more about your specific use, then, of these structures, because you look into photochemical and photophysical reactions, so reactions that really need the presence of light.
Yes. One of the interesting things in photochemistry is that you can shine light on a molecule and it becomes excited. It absorbs the light and it becomes excited. And those excited states then undergo different reactions or use that energy, the energy of the excited state, in different ways. The actual properties of those excited states depends very much upon the environment in which they're sitting, and also how easily they can meet other excited states, other excited molecules, and react with them. What we have been doing is trying to incorporate those molecules which can be photoexcited within the metal organic framework. You are controlling the environment of the excited state, of that excited molecule, and also you're stopping it meeting other molecules, and therefore you're changing the properties of the molecule by putting it within the framework. And metal organic frameworks are ideal for this because you can design the framework structure, as we've just been discussing.
What is the benefit then, say, of keeping them in this rigid state, say, and analysing what does happen to them?
It gives you real insight into what is the nature of this photoexcited state. Probing those excited states is difficult because many of them are short-lived. They can be less than a nanosecond, and it can react, it can undergo chemical transformations, it can do all kinds of things. You need to understand that process. But also, by putting it within the framework, we can prolong the lifetime of those excited states. We can change the actual properties, in fact, and actually we can probe them differently. Often, the way that you look at these excited states is by using spectroscopy. They give you lots of information, but it's not quite the same as the detail which you can get from other techniques, such as crystallography. And this is where our work with diamonds comes in. At diamonds, we can get what are called crystal structures of single crystals of our frameworks using the sort of high-energy X-rays that can be generated at the diamond synchrotron, which we can't do in our own labs here. What this allows you to do is to actually get detailed information about the precise positions of the atoms within our molecules. And this allows us to actually see what happens to the photoexcited state after it reacts.
Could you give an example then of a particular reaction that you have been looking into at diamonds, say?
A particular case, we can incorporate within a framework structure a particular rhenium complex. Now, rhenium's a pretty unusual metal, and this particular type of rhenium complex has been widely studied and is actually used, it's kind of a classic of photochemistry, and has been used in all kinds of different applications and studied in solution, looked at how it interacts with DNA. It's been used in photovoltaic applications. What we did was we incorporated this basic group within a framework, modified its properties, and were then able to look at how it behaves after photoexcitation.
And what would the next step then be? With a really thorough understanding of this process, say for the rhenium complex and other examples and other reactions as well, what would it then be hoped would be the next step using this information?
In this process, there are carbon monoxide molecules attached to the rhenium center. And actually, on photoexcitation, there is a short period of time where this carbon monoxide molecule comes away from the metal center. And there's what's called a vacant site. Normally, and indeed in the studies we've done so far, what happens is that the carbon monoxide goes back on. What we really want to do is to prolong the lifetime of that situation where there's this vacant site on the metal and try to put different things onto it. There are two directions here. One is that you could try to put alkanes onto there. So this is things like methane gas, and try to incorporate it and get a rhenium to methane interaction. And that leads to what's called activation of the alkane and make it react differently in chemical terms. But the one we'd love to do is to try to put xenon onto it, try to make a metal to xenon bond and actually characterize it so we know exactly where this xenon is sitting. The xenon is incredibly unreactive. So actually being able to identify and characterize a bond to xenon, it's almost one of the holy grails of chemistry.
So it would be quite an advancement in kind of fundamental chemistry, really, to try and get this bond.
It's fundamental understanding here. I mean, it gives us a far greater understanding of how these things can behave. It advances science altogether. There is still a beauty in understanding how different atoms interact with each other, because that's the basis of all chemistry.
Professor Neil Champness from the University of Nottingham. Now that is it for this month's podcast. But we'll be back in March with more news and events from Diamond. In the meantime, if you have any questions about the facility, the research you've heard about in this podcast, or if you simply have any suggestions for what you'd like to hear more about, email podcast@diamond.ac.uk. Thank you very much to Trevor Raymond, Sarah Bucknell, Charles Cockell and Neil Champness. I'm Mira Senthilingam, and thank you for listening.
The Diamond Podcast is brought to you by Diamond Light Source and produced by thenakedscientists.com. There's more information on our website at diamond.ac.uk/podcast.